Hi, and welcome to Circuit 3B, where we will continue our study of motion with this component, an ultrasonic distance sensor. This little guy can sense how far away an object is and communicate that to our IoT breadboard electrically. How does it do it? Let's find out. You're likely familiar with the fact that bats use echolocation to identify objects in low light conditions. They emit high-frequency sounds using their mouths or noses, which then bounce off of objects and return to their ears. The reflected sound waves that they hear are called echoes, and by analyzing the echoes, the bats can determine an object's distance, size, and direction. If bats are constantly emitting high-frequency sounds for echolocation, why aren't they super loud animals? Well, the sound that bats use for echolocation is actually at such a high frequency that it is above the range of human hearing, or ultrasonic. Electronic distance sensors work in much the same way as the bat's echolocation. They send out pulses of light or sound from a transmitter and receive it with a receiver in order to determine the distance of objects. The distance sensor in your kit is an ultrasonic distance sensor, so it emits ultrasonic sound with the transmitter, labeled with a T, and then receives the echoes with its receiver, labeled with an R. The sensor has 4 pins: power, ground, trigger, and echo. To signal to the sensor that we want to take another distance reading, we send a high pulse on the trigger pin. This will cause the sensor to send a burst of ultrasonic sound from its transmitter. When the echo bounces back to the receiver, the module will output a high pulse on its echo pin. The pulse width of the signal from the echo pin is proportional to how far away the measured object is, so a longer pulse means that the object is further away. By reviewing the sensor's datasheet, we can determine the exact equation to use to calculate distance based on the pulse width on the echo signal. That's about it for theory for Circuit 3B. Now let's build the thing. For this circuit, we will recreate our RGB LED hookups from Project 1 with the RGB LED and current limiting resistors. Then we will hook up the distance sensor with its power and ground and connect its trig pin to digital pin 20 that we will use as an output to deliver the trigger pulse. Finally, we will connect the echo pin to digital pin 21, which we will use as an input to receive its echo pulse. Remember that we are using 5 volts for our power rail in this circuit, as the datasheet for our sensor says that is required. Let's scroll down and run some code. First, we will set up all of our pins, including setting the trigger pin as an output and the echo pin as an input. Next, we will create a function that uses the equation from the datasheet to convert the pulse width on the echo pin into a distance. Notice the use of the time pulse microseconds function, which is built into MicroPython and allows us to easily time how long our echo pin is high. Finally, we use the distance of objects to turn our RGB LED different colors. So when I run this cell and slowly move my hand towards the sensor, we'll see the RGB LED change from green to yellow to red. Feel like Batman yet? We've just used ultrasonic sound to sense the distance of objects, just like bats do. We're not done yet though. Stick around for Circuit 3C, where we're going to be upgrading our distance sensor and putting it to a practical use.